Hello, welcome to the Introduction to Model Checking Lab 1. In this video we'll just go through the introduction to the new lab. And basically we're just going over the theory that you have covered already in your lecture slides. Just so we have a recap before we start into the questions. So introduction, this lab focuses on the basics of model checking. So we've seen this diagram before. On the left hand side we have our requirements, which we formalize, and we get our property specifications. This is done using temporal logics, or as I say, a mathematical language, which is denoted, as you see here, by the phi symbol. And on the right hand side we have our system, which is then modeled, and we come up with our system model, and it's denoted by our M here. And we see that the model checking process determines whether our model can satisfy our formula. And if it's satisfied, it says so, and if it is not satisfied, it says it is violated, and it gives you a counterexample as to how the model does not satisfy this formula, phi. This is just a general overview. We'll go into it in more detail. So model checking is an automated method. Once given a system model and a set of formally specified requirements, as we see here, that checks whether the model satisfies the formula, so it is correctness. System models come in various perspectives. However, in terms of these labs, we will focus on labeled transition systems, or labeled transition systems more like, Kripke structures, and their combination, the Kripke transition systems, or KTS. The system models ideally have a finite number of states in order for properties to be satisfied. However, this is not a strict constraint, and often Kripke structures are infinite. But basically what this means is if you're traversing a model, ideally you want to have a finite number of states so you can actually determine that the whole model satisfies this formula, if you were trying to determine the whole model does, or part of the model satisfies this. But this is not a strict constraint. These models can, in theory, be infinite, and often are infinite. And when they are infinite, you get a thing called, you can get a state explosion problem, which refers to a model that has a seemingly infinite number of states in order to represent all possible behaviors, and is here where binary decision diagrams, where we saw in our previous labs, or BDDs, are commonly used to represent transition systems more efficiently. So as you saw, we were able to, with our decision trees, we were able to apply our tree rules to reduce the number of nodes and terminals and etc., and reduce our memory space required, and also increase our time for classification. So BDDs, or decision diagrams, are quite common in the model checking world, as you're able to actually check, say, the root of one binary decision diagram. You can check if it exists in another existing BDD, and then from there you're actually able to check whether the other model has the same pathways as your current BDD. However, we will not be going into BDD model checking currently. So, formally specified requirements are more commonly referred to as properties. The most common properties to be checked concern reachability. So if you have a number of states, if we just show, so if you have a number of states, can all these states be reached? Safety, so to ensure that nothing bad happens within your model, such as two, let's say, parallel programs entering a critical section. Liveness, which is that something good always happens. So a model can be safe, but it can be safe because it actually never leaves the initial state. It just stays there forever. But that means nothing good actually ever happens in your model. So you got to ensure liveness as well, that it actually does transition and does move, and has behavior which we want. and fairness, which is basically means that if you did have a parallel program, that each one actually gets the opportunity to execute, and it's not just one program executing over and over again, that you actually allow other people the chance to have liveness, if you like. These properties are typically formalized using different forms of propositional temporal logic, which must be satisfied by the model to ensure overall correctness. States within the models contain atomic propositions. So atomic propositions, again, are Boolean values that must be either true or false, which, when combined with temporal logics, result in a formula which can be formally checked to ensure the properties are satisfied. So basically what we're saying is each state will have an atomic proposition, which is a statement that is either true or false. It's either yes or no. And our temporal logics allow us to traverse the model, so go from state to state to state based on what you want to do, whether you want to check all the states or just a certain path, depending on which logic you have. And you're just going to determine whether dim atomic propositions hold in every state on that path. That is essentially what we're doing. If a model checker determines a formula is unsatisfied, aka you want to determine an atomic proposition is true or it holds throughout an entire model, and you find a state where it's not true, that would be a counterexample, and it will return to the user how the violation can be reproduced. So return all the paths or all the states in the path that led you to the violation where it's unsatisfied. So you're able to actually reproduce and show in your model where your issues are. The temporal logics we will be using within our labs are linear temporal logic, or linear propositional propositional linear temporal logic, PLTL, and computational tree logic, CTL. We will go through these in the later section. Model checking can then be surmised as an approach to verification problem which formalizes. So the verification problem is, does your model do what you think it's going to do? Does the system satisfies property? So we have properties, does your system satisfy it? As in, Kripke structure, which is a type of system, is a model of a temporal formula which represents our property. So this is what we're saying. So in the system we can have a Kripke structure, we can have a label transition system, etc. Is a model of or satisfies property, and this can be represented as a temporal formula, either using PLTL, CTL in combination with atomic propositions. So this is what we will be doing in our next few sections. Thank you.